And work and energy questions. Go ahead, ask me. I think I even know those off the top of my head, but I might try to look them up.
Okay, the first one says, we assumed that the distance that the rod moved was proportional to the work done by the driver. Why is this a reasonable assumption?
Yeah, okay, so the definition of work was force times distance.
Mm-hmm.
Okay, and in that experiment, we're pushing that nail down.
Mm-hmm.
And so our work is the distance the nail moves times the amount of friction. And the reason then to answer the question is we left the friction constant.
Mm-hmm.
And if you remember me doing that, I'm your lab partner. And so I adjusted the wing nuts at the beginning and then I left it that way. And so that means that the friction stays the same throughout the experiment. So distance would be multiplied by that friction in order to get work. And so the short answer is because the friction remained constant.
Okay.
Which means if the nail moved 1 centimeter, there would be 1 times some number. We don't know what that number is, but let's just say it's 100. So I would have, 1 times 100. But then if the nail moved 2 centimeters, then I would have 2 times that same number. Mm-hmm. And it would now be twice as big. So you can use distance as an indicator of work. It's not a real number. 1 and 2 are not the same number as 100 and 200, but they're the same pattern and the same proportion. And so when you make a graph, you see the same effect.
Okay. Okay. Thank you.
Oh, is that the only one?
Well, I guess number 4, it says summarize how mass and height affect potential energy.
Oh,
and good. I'm just wondering if I've made like I said, as the mass increases, the potential energy increases, and as the height increases, the potential energy increases. But I'm wondering if I have to do more than that to summarize it.
Those are good answers. So in terms of getting credit, you don't need to do more. But let me expand more because I'll say something here. So question number 2, says, how is the work related to, and I believe that's height, right? Or is that mass?
Fall distance, yeah, so height.
Fall distance, height. Okay, yeah. So you just said as one increases, the other increases. Okay, but we can do a little better than that. If you look at the graph, it's a straight line.
Mm-hmm.
And so that's a little more than just increase, because there's a lot of graphs that increase. When it's a straight line, it's called proportional.
Okay.
Meaning if
so
one
I
doubles,
could say it increases proportionally or something like that.
Yeah, that would be a stronger statement. To say that the height and the energy are proportional.
Okay.
And then question 3, which is the same question, but with mass. And again, instead of saying they increase, say, well, because they're a straight line, they are proportional. So that's a little stronger statement.
Okay.
And then your question about number 4 then just is really putting those two together. You could say that it's, I would use these words. I would say it's proportional to both the height and the mass.
Okay.
And of course, that's the equation we have.
Okay, thank you.
Okay, awesome. Zoom. All right, good. All right, so, oh yes, and so let me share my screen here. And that connects, nice. It didn't ask me for a plugin. Maybe they fixed that little bug. It was weird I never did this last spring. Every time I but we got a new version of Zoom right before the semester started. And the first day I hooked it up, and then I went to hook up the phone, and it said, "Oh, you need a plug-in to connect your phone." And I was like, "Oh no, what?" Now, fortunately, I just had to hook on the plug-in, and it downloaded like 3 seconds or something, and then it went like, "Okay, well that's good." And then the next week, it when I started it up again, Zoom, every time I started Zoom, it said I needed the plug-in for the phone, and I was like, "What?" Anyways, this is the first time it hadn't done that, so I would maybe the people at whatever Zoom decided to make it permanent. If somebody does the plug-in, keep it installed. All right. Anyways, let me come back to this question and read it here. It says this: an oceanographer is studying how the ion concentration of seawater depends upon depth. And actually, this would be a great way, because the conductivity would change in connection to the ion concentration. And so by lowering a probe in there and just measuring how well does it, we'll make that solid, how well does it conduct, would tell you something about the ion concentration. All right, so I'm going to try to draw a coaxial cable that they've got. They call this inner radius RA, and then they call the radius of the outer one RB. I suppose we probably should use the phrase the inner radius of the outer conductor and give it a little thickness. I see that the drawing doesn't, so there really is no distinction then between the inner radius of the outer conductor and the outer radius of the outer conductor. And that's all we care about, is that inner radius. So that's our B. The little probe she's making has a length of L, and that's what it says here. She makes a measurement by lowering it in water in a pair of concentric metal cylinders at the end of the cable, and taking data to determine the resistance between the electrodes as a function of depth. The water between the two cylinders forms a shell of radius RA and an outer one of RB and of length capital L, which is considered to be much larger than R sub B. The scientist applies a potential difference of delta V between the inner and the outer surfaces, producing an outward radial current of A. Let rho represent the resistivity of it. Find the resistance. Okay. So I guess I would start off with that. Find the resistance. And this chapter was saying that the resistivity depended on 4 factors. One of them is the function of the material itself. Another one is the length of the material, and the other one is the cross-sectional area. Oh, and by the way, the fourth one, not real obvious in this equation, is that the resistivity of the material depends on temperature. So the material, the temperature, the length of it, and the area. Now, here's where we're going to have to do a little bit of calculus, and which makes this one of the harder problems of this chapter. And I would probably classify this as the easiest chapter we've done this semester. Not even to call it easy, but we've done some pretty hard chapters, and this is probably the easier one. But changing this into what I'll call a calculus form, if we just took a microscopic length, and so call it a DL for a small microscopic length of copper or aluminum, and whatever cross-sectional area we had, that would give us the microscopic resistance for that So this problem, by the way, is a lot like another problem that I think I did do last year on Zoom. Yeah, it's the one right below it, 56, where you take a cylinder that flares out. So it's more like a cone. And I'm going to draw it on the side. In 56, they have it standing upward in this position. But just to kind of give you kind of a helpful hint as you run through that video, or even on your own without the video, again, the idea is to chop it into these slices, kind of like something that's tapered and you're cutting it, maybe a carrot, so carrot's got a little taper to it, and then you're cutting the carrots, and each little slice then is kind of a coin shape that gets bigger and bigger and bigger as it flares back. So the way to do that is, of course, to say, let each slice have a little resistance. And so the total resistance is what you're going to get when you add them all up. Now, maybe I shouldn't have spent too much on number 56, but I think it's easier to see the slices on 56, and I wanted to give a hint towards 56. Our problem, I would call the slices shells. And so maybe in green, I'll make a shell and cut it microscopically thin, and then apply this right here and say, okay, what is the resistance of that microscopically thin shell? Because then I'll make around it another shell. Maybe I'll color that one in red. Something like this. And anyways, I'm going to add those up. Now, by the way, the reason I know I need to do that for both this problem, which I guess is 52, and the one I was talking about, 56, is because the resistance depends upon the area. And so this was derived for something that had a length and a uniform cross-sectional area A. And then seeing something like this, which is a bit harder than we derived in the book or in the lecture, I'm going to have to make the statement that, okay, I have to add up a bunch of pieces because each little piece has a different cross-sectional area. So in the case of 56, if I drew one little kind of disc-shaped object from cutting this carrot, whereas this one, actually this one I can probably illustrate really well with the Post-it notes. So the first little shell, maybe I better make the first one, which I've kind of colored in green, kind of tight. And so I'm asking myself, okay, what is the resistance of this? So that'll be the green one. And then the red one I'll add to it. So the red one gets wrapped on top of it. And I'll do a third one, but I think you're kind of getting the point here that I'm just going to add a bunch of shells, and a very common procedure I'm sure you've seen in your math class, and you just keep adding up the shell. So that's essentially what I'm doing mentally, is saying, okay, I've got a green shell, a red shell, maybe I'll have a blue shell. Anyways, I just keep adding up shells until I fill in that whole surface. And each one of those would have a set amount of resistance. So if I were to ask myself, what is the resistance of one of those shells? I would say, well, it's the resistivity of the material, which in this case would be seawater, and times its length. And here's how we need to be careful, because what is the length and what is the area depends on where the current is flowing. So they are saying that the center electrode gets charged up positive and the outside negative. So the current flows radially outward. And so in this derivation, the length L is the direction that the current flows. And so I know a lot of times when you look at a cylinder like this, go back to my little set of wrapped up Post-it notes here. A lot of times we call this the length of the cylinder. And so if I'm calling this the length of my resistance, you might mix those two and think I'm talking about the length of the cylinder, and you might want to put a capital L here, but that would not be correct. The L is the length along the direction that the current is flowing. And so we need to know how the electrodes are hooked up. And so that's why I'm glad, even though it was kind of a long worded problem, they made it very clear that there's a potential difference, delta V, between the inner and outer surfaces. So they even go on to help you and say, this then produces a radially current. So the direction of the current is this radially outward. And so it would be, out, 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 out. And so that means this little microscopic distance that the current flows is really a dr. That's what I want to emphasize. Is what do I put here? Do I put a length along what we often call the length of the cylinder, or do I put it along the radial direction? And the answer would be the radial direction, because that's the direction that the current flows. And so that's why, by the way, in 56, if you took this and cone shape and put it on your object, they tell you that the current enters this smaller part of the cone and then exits the bigger part of the cone. So this direction, which I'll call X, would be, the length. And so in 56, right here, in place of DL, I'd put a DX. But again, probably saying too much on 56. So on 52, then this becomes the DR. And then the area, this is the area which the current is flowing. So again, if you take one of these shells, and maybe I'll just unwrap the last one and just hold the last one by itself. Maybe look straight down the camera. As we said, the current is going radially outward. So the area would be the actual area of this shell. It would be the area of this Post-it note. So if I unwrap the Post-it note, its area would be this dimension by this dimension. So I'll rewrap it and point out that this dimension here is its length, and this dimension here is its circumference. So I would have the circumference times its length, which we called it L. And of course, in this case, I mean the length of the cylinder, not the length of the direction that the current flows. All right, so in here where I want to put area, I would put 2 pi r L. Since this is the one dimension of the Post-it note, the circumference, and this is the other. And so that's how I'm going to get the total resistance. And then that's what A is. Find the resistance of the water between in terms of, and then they say currents, resistivity R1 and R2. Okay, so I'll continue here and say, all right, the total resistance means I need to add up all these shells. And the first one is at RA, and the last one is at RB. And so now the math can begin. And so like any good math problem, especially involving calculus, let's simplify it. And in this case, things that are a constant, like the resistivity, the 2 pi, and the length. Every little shell that I'm adding has the same length. And so now I'm just left with an integral of dr over r, evaluated from A to B. And so this becomes the resistivity, 2 pi L. And fortunately, this is a pretty straightforward integral. This would be the natural log of R, and then we would evaluate it from RB to RA. And taking advantage of the properties of logarithms, you subtract two logarithms, you could write it as a quotient. All right, so there's the resistance. I don't think I quite answered it because it says find the resistance of the water between in terms of, oh, I guess I did, L, I got an L, and rho, okay, I did, and RA and RB. All right, so so I guess I have done step A. Now, step B is kind of more to this chapter, if you will, because then it says find the resistivity in terms of the things that you would actually measure. So I'd say that because when you actually run this experiment, you're probably not going to measure the resistance. What you're probably going to do is build it so you will measure RA, RB, and L. And instead of measuring resistance, you would measure, of course, the currents and the voltage that you hook it up to. So with that in mind, let me put Ohm's law here that says voltage is current times resistance. And in this problem, they call the voltage delta V. So I'll use the delta V. The truth be told, all of our V's are delta V's. So when it's kind of irrelevant how we mark that, but I'll follow their pattern, delta V. Then I is, like I said, probably a measured quantity. Yeah, so you'd probably have an ammeter. You probably have a voltmeter and ammeter up on the ship's deck as you lower this in. And then, so I'm going to just use the results that I got in part A for the resistance, which is the resistivity over 2 pi L times the natural log of RB over RA. And now just solve for the resistivity, express the resistivity. So let me put the 2 pi L on the denominator over to the other side in the numerator. And then let me put the current over here and also the natural log. Excuse me. Oh, neat. So there's the I, and then anyways, there's the resistivity. So there's part B, finding the resistivity, which is incorporating Ohm's law. So that's probably the easier of the two steps. This is the tough one, adding up a bunch of pieces. Throwing our calculus at you.
Cool. Yeah. Thank you.
My pleasure. All right, let me jump back over here, see if there's anything else or anyone in the chat. Nah,